So resilience, there will be problems that you can't solve. There are problems that I still have no idea how to solve. But you know, I don't look at that and get upset about it.
I'd like to say there's no miracles. Like, you've got to put in the hours.
If you're able to just get over that mental hurdle of the fact that this is difficult and say, I want to enjoy it, I just want to understand the physics.
So because we want an angle theta of 90 degrees here at a height ZS, we can substitute this in.
Specifically, it turns out that this arc is actually a circle when the speed variation is linear. And we're just trying to see if we can figure out a nicer way of doing it. The standard way is to split the path into small segments of dx.
I'm here with the chair of the British Physics Olympiad. Thank you so much for inviting me, Robin.
It's a pleasure. It's good to see you here. This Trinity training camp. So this is a training camp we have in Cambridge for the team. We also happen to have the German team here at the moment training with us. You might think, well, what do we do in collaboration? I guess sympathise with each other. So these 12-hour days we're experiencing, a 5-hour practical, a little break, and then a theory session for another 2.5 hours, then dinner, then another theory session till 9 o'clock in the evening. So it's quite good to sort of be working with others and all in the same boat, and it's just quite interesting that way.
Absolutely. And the students who are here now, they've gone through quite a rigorous selection process, haven't they?
Well, they have, I guess. Yes, it's good to start problem solving early. And this is not sort of really difficult problems. Those certainly crop up. But it's a matter of developing those skills of, what are the skills of problem solving? Well, it's a certain amount of determination to keep going. Rather than just sort of, I've had a quick think about it for 5 minutes. I can't really see it, so I'll have to ask somebody what the answer is. And if you spent a couple of days in it and you haven't quite got it, then it's just worth talking to people about it and why you're stuck. And what you really get from problem solving is being able to work out why you are stuck in a problem, because that is the way of developing those skills of asking questions, getting to grips with what the problem is asking you. Why have you not been able to see it? You could say, well, maybe it's just too mathematically advanced. Well, that's a different matter. There are plenty of physics problems which are not mathematically very sophisticated, but they're still difficult. And is your understanding of the ideas in the physics quite clear-cut, or you've got a slight muddle of them, and therefore the question doesn't sort of fit into your sort of way of thinking.
And would you recommend the students use the mark schemes after a couple of days of being stuck? I like how you said talking to people, because I found that I learned the most from other people compared to mark schemes.
Yes, the mark scheme tells you the answer, and it tells you sort of the steps along the way, and that's very nice. But is it going to help you solve the next problem, which won't be the same one, obviously? What are the skills that you kind of need to have for problem solving in general? And it's just that sort of persistence and being willing to sort of take the whole problem and get it in your head, which means drawing a diagram. So you have all the symbols in the diagram and the diagram set out. You've checked you've got the right diagram. It's kind of not exactly to scale, but it has the right sort of characteristics. So it's no good sort of drawing a square when you actually are discussing a circle and trivia like that. So it's very important to have that diagram, because the diagram you can see in your head, whereas all the wording of the question you can't see in your head. You have to go back to it and sort of look, and you've missed the fact it's frictionless, or there is friction, or the slope is quite a small angle slope, or things like that. Whereas when you draw the diagram, it's there, you've got that detail out, you extracted it, and you've got it on the paper, and you can see that diagram in your head. You can talk to a friend about it, and you can discuss the diagram, because it's the same thing as in both your heads. Whereas with wording, you might have some idea what the wording is, because you can kind of just about remember it, and your friend has a slightly different view of the wording, and so you're talking about different things.
I think that's one of the reasons that I use the British Physics Olympiad extensively in my teaching practice, because those are the type of skills which are a lot harder to recreate from A-level problems, simply because a lot of the times the steps might be, a couple, maybe 3 or 4 steps between problems. But I think Olympiad level problems force you to become a better physicist. So
yes, in many ways, yes. It's of course, physics problem solving for the Olympiad is a bit of a specialist skill because it's a competition. You're meant to do it reasonably fast, and I'm not a particularly fast problem solver. I like solving problems, a bit like doing some of the puzzles at the end of the newspaper. But doing them fast, that's something you do when you're slightly younger than I am, and there's no particular need to do them fast unless you're actually entering competition. But to have that sort of persistence in doing them, because if you're going to be a physicist, you're going to solve problems. And once you pass sort of undergraduate level, where you're given questions to which the answer is known, practice problems, once you get to research level, the answer isn't known, you are finding it out. And it's no good saying, this is quite a difficult problem. I wonder who's going to tell me what the result is. You are, after 2 or 3 years of work, research, thinking about it, doing some experiments, getting someone else to do some experiments and finding out what the results are, and discussing it with a group of people. This is why you have international conferences, so that people working in that area can actually come together over coffee or something, and they discuss the ideas, what's going on, what progress they've made, why they're stuck, what good ideas they have. And that is where you have the sort of, the breakthroughs, because you're opening your mind to some new ideas. Certainly in problem solving, you can experience getting stuck in the problem, and if you just keep going, sometimes you just can't solve it. You get stuck in a rut, and you just need a break sometimes. I mean, it's possible to just keep going, and eventually you just see it. But quite often, you're just digging deeper, and it's not a particularly difficult problem. It might even be one you've seen before, but you just can't quite see it now. So you have to have a break, and you can do something else, and you could discuss it with somebody. But if it's not really all that difficult, you have that break, and then you come back to it later, and sometimes you just see it. It's just you're out on the plane again. You're not stuck in the hole, and you kind of see it. Oh, this is just how it's done. That's what the brain does for you. I have no idea how it works, but
I remember this at university, just suddenly taking a walk and just kind of all realizing how things kind of fit together.
It is. It just, you don't know what it is, but it just sort of suddenly, it's clear and you just do it.
And is it quite hard coming up with these problems? It's one of the things that I always wondered when I was going through some of the round 1 Olympiad problems. Some of them are so creative.
Yes, I mean, it's very hard to sort of have, at this level, at sort of the school level, a really original problem, because it's been going for so many years. It's difficult, but they are tuned to your audience. So, for example, our round 1 questions are sort of tuned to a sort of A-level audience, rather than sort of an undergraduate university audience, or someone who doesn't quite fit in, because the wording's got to be right, just the amount of information you give. I mean, you could make questions much more difficult by just wording them without giving any idea what the entry point is. And it's the same question, it's the same information you give, the value of G, Planck's constant, all that sort of stuff. But if you don't it's sometimes the way you think about it. You think of a question and you follow a track, and then you present it as the question following that track. And it can be leading the student along, so step by step they sort of make progress. But you can sort of word it so it's kind of almost backwards, and it's the same information, but it's just made unclear as to how you start.
I also think that because of that, I always really, really encourage students to take part, because in that process that you're describing, very often the Olympiad problems tend to either showcase a beautiful piece of physics. All the International Physics Olympiad problems seem to feature around amazing physics, which is very often beyond A-levels things like the 2-3 body problem, which are very rarely covered, but they feature in Olympiad problems. And it's one of the ways that you guys can experience this much earlier, and also get an appreciation of doing physics for kind of the beauty of it, which it sometimes can be overlooked in school, I find.
Yes, yes. I mean, you have sort of several years of just doing physics stuff in classes, and you think, I'm not exactly at the forefront, at CERN, it sounds exciting every day. I'm thinking about, tomorrow we'll probably discover, the successors to the Higgs boson and things like that. It all sounds very exciting. What do those people do? Well, those people have sort of trained hard by attending the usual school physics lessons, then they've attended more lectures at university, then they've done some research, which they open up books and actually study them and sort of see how the techniques can be applied to their activities. And it is hard work. It's very satisfying. I mean, actually, on the small scale, solving a question at school can be momentarily satisfying because you kind of finish the prep and all that sort of thing. When you have an Olympiad problem, it's meant to be difficult. It's not impossible, but it's meant to be a sort of challenge for someone of your age. And when you solve it, it is very satisfying because it was given to you as a challenge problem, not something just to sort of pass the time. So that is very important. You want that satisfaction. You don't want to sort of gloat over it. I mean, it is a sort of passing thing, but that feeling of success on these small things, it builds up, and you realise, well, when I get a sort of even more difficult problem, what physicists call a more interesting problem, you could actually give that a go. You think, I'm not sure I can solve this. I just don't know enough. But sometimes you do. Sometimes it's just not made. So, introduction. This piece of information, Archimedes' principle. So you could work out and so and so. But if you don't say any of that, you just say, so the ice on the South Pole all melts. What's the sea level rise around the planet? You think, don't I need to know something? Yes, but you can make some estimates and you can actually get somewhere with it. Maybe not an accurate answer, but physicists can do a lot because they solve problems so they can solve other problems even when they think, this is tricky, but it's worth thinking about. Let's see what progress I can make. And I might need to sort of ask, what's the size of the South Pole ice mass? Something like that. But the rest they could do, and we could do it at school.
That's absolutely fascinating. Robin, thank you so much for having me. Absolutely incredible weekend. I've personally learned a lot, and best of luck in Paris.
Thank you very much.
I'm sure you will come back with medals.
Well, a week and a half we'll be there, and then yes, fingers crossed. I mean, it's really nice to get medals. It's not it's not of national importance. It's important to the individuals. It is very nice, but taking part is a great thing, and they come back with a good knowledge of physics, and actually many of them come back, and next year they will be helping to train the team because they got that confidence that they can talk about these ideas, not know everything and be super sharp in an instant, but they will they enjoy the physics, they enjoy discussing it with others and developing those skills.
How was your 5-hour practical?
It was okay. I think it went pretty well. Managed to make some good progress.
What do you think is the difference between a A-level practical and a International Physics Olympiad practical?
In an A-level practical, you'll usually be working in a group, and there'll usually be the teacher looking over you. Whereas an Olympiad practical, you've got to look after yourself, manage all your own stuff, so you've got to work your independence a lot more.
And excellent. And how did you get to this place to be selected for the International Physics Olympiad?
So I started by doing the Olympiad round 1 back in November, I believe.
Okay.
And then I did well enough to do the Olympiad round 2s in February or March. I can't
When did
remember.
you start preparing for the round 1? Out of
So
curiosity?
our teacher started doing some, like, during the school, during break and lunch, some preparation sessions weekly when I went
Okay.
back for year 13 from September. So I had a couple months of those before round 1. And then kept doing problems like in physics lessons once I finished all the extensions and a few at home.
Were you doing
until
loads
now.
of independent study out of school hours?
I did a bit, yeah, just to do a mix of problems
Okay.
and have a look over the topics.
Yeah. What sort of advice would you give for just general problem solving to people preparing for Olympiads?
Don't be intimidated by the problem.
Yeah.
Read through all the words they give you very carefully, because usually there'll be a clue in there. They won't expect you to know something you haven't seen before. There'll be a clue, so you just have to find it.
Excellent. What's your favorite topic in physics, out of curiosity?
Ooh, I really like dynamics and
Dynamics.
kinematics. I just find the problems really fun to
Very
solve.
good choice. And how do you think the difficulty of Olympiad problems compares with A-level problems?
So A-level problems, you're usually going to be given the data that's going to go straight into the equation you need. So you're not going to have to look very far, much further than the formula booklet. Whereas the Physics Olympiad, stuff is going to be set up so you have to work out a lot more and try and work out how you put things into equations, which is most of the challenge of a Physics Olympiad problem.
Fantastic. Are you doing physics afterwards, do you reckon?
I've currently got an offer for an engineering degree.
Oh,
so
amazing.
yeah, quite a bit of
Excellent.
physics there.
Well, best of luck in France.
Yeah.
And yeah, any other last-minute advice that you might want to give for somebody in your position next year?
Feel free to give it a go, the Physics Olympiad, because there's not really any stakes. You just turn up and try, and even if you don't do very well or don't get a medal, you still have fun trying to solve those problems, and that's something that's going to be useful.
My name's Harrick. We're in Trinity. We're in the physics department in the University of Cambridge.
And you've just done a 5-hour practical as a selection process. So Harrick here will be going to Paris at the International Physics Olympiad. And yeah, how do you get to this place?
There were 2 rounds of tests and then a selection camp in Oxford. So 3 different stages. And after that, I got selected, and that's why I'm here.
And when did you start preparing for the Olympiad, out of curiosity?
I started preparing around April last year.
Okay.
So just after mock exams last year in year 12.
And were you doing loads of round 1 papers?
Yes, and I was doing a variety of different country Olympiads, just a variety of different stuff online to get a feel for Olympiad physics.
That's amazing. Excellent. And why did you put all this extra time into Olympiad problem solving?
Because I had nothing better to do.
That's amazing.
This is really fun and enjoyable, and I had some time aside from studies, so I decided to do more studies and do this.
Okay. Yeah. Amazing. Excellent. And how did your A-levels go?
Pretty good. We haven't got results yet, but they should be
Yeah.
pretty positive.
If you could give any advice to any future A-level students, what would you say? What do you reckon?
Just go for it. Don't doubt yourself. Just try your best, and you'll probably make the team if you're committed enough.
Where are we right now, guys?
We're at the Ray Dolby Centre in Cambridge, and we're here for the Physics IPho training camp.
And what's your day been like so far?
It's been quite intense. We've just done a 5-hour practical, and I think we're all a bit shattered. Yeah.
I mean, it was better than yesterday's, so, but no, it's exhausting, and then we are following up with long 2-hour-ish theory sessions after this.
How many days are you here in total?
5 full, is it 5 full days?
I think
5 full days. Yeah, 5 full days and then some half days.
And very intense days, like 12-hour days.
Yeah, we
non-stop
kind
physics.
of start at around 10 and then run until 9-ish. Yesterday we ran over by 40 minutes, so we got back
Oh wow!
at 10.
Oh wow! What sort of theory were you doing?
So yesterday we did magnetostatics
Okay.
and some thermodynamics, and today, I don't know what we're doing today.
we're doing waves and then orbits.
Yeah, fantastic.
Should be fun.
And you guys have all finished just your A-levels just now.
Yeah.
Any advice for future A-level students that might be watching this in the future?
I'd
or
say
now?
just try and enjoy the process. I'd say enjoy the process. It's really good fun, and just get it over with.
Yeah.
And it will.
Learn to think critically, not follow a mark scheme, I suppose. Although there is always a degree of learning mark schemes.
I also think with A-level, a lot of it is consistency, like do a little bit throughout the year and you'll find so much of the work done for you by the end, rather than cramming, which I know can be like tempting, but it's like good practice.
Couldn't agree more. And any problem-solving advice? Because obviously you guys are at the top end of problem solvers. So how did you prepare to, how did you develop your problem-solving skills? When did you start preparing for round one, for example?
Shall I answer this one?
Yeah, we're going to answer it.
I suppose, like most things, practice is an important element. Practice and consistency, which again goes for most things. If you want to get better at problem solving, the best thing to do is solve progressively harder and harder problems over the course of years, really. If you want to, I mean, round one, I only, I suppose, started preparing for explicitly maybe a month, maybe two at push before, but long before that I was doing kind of difficult physics problems at kind of close to that level.
What inspired you to do those problems beforehand?
I think part of it is interest. I guess I suppose another part of it might have been competitiveness. That being, the problem is with that is that can't drive you forever, because eventually you get to this point where you're competing with some incredibly smart people, and it's very difficult to keep up. Does anyone else want to?
Yeah, any problem
I'd like to
solving
say
advice?
there's no miracles. Like, you've got to put in the hours in order to get to that stage, and there's no secret. It's solve problems, start simple, and find the level that's right for you, and then eventually you'll look back and you'll wonder how you've got there, really.
And out of curiosity, were you solving problems from the British Physics Olympiad website, or where was your source of problems? Like, if I was to be preparing to take it next year, where do I start?
I mainly just did BPhO past papers.
Okay.
Round one, and when I was comfortable with that, I did a few round two papers as well. And then there's like an upgrade your physics book,
Oh, yeah,
which
yeah.
is like
It's fantastic.
recommended.
Yeah.
And like I actually
It's
found that
amazing.
very useful, because like you have to know things and be familiar with things that aren't in the A-level syllabus, and you have to be able to like understand those concepts. And there's not many sources that are designed for like sixth form students that are not like assuming some undergraduate knowledge. And it was very useful for me, and it was a good starting point.
What about differences in practical work? Join in.
I'm Henry.
Do you want to just pass the microphone? So, yeah.
I'm Henry.
And how did you find the practical?
It was hard. It was harder than the previous ones.
Okay.
Yeah.
What's the difference between an A-level practical and an IPho practical?
It's much longer. It's much more difficult.
You're on your own.
And yeah, you've got no idea because in an A-level practical you kind of know what the result's going to be already. Whereas here you've got no clue if you're correct or not.
Which one is the more fun though?
No, this one is more fun. This one is more fun.
It's more fun if you get the correct answer and you understand. If you understand it, then it's more fun.
Well, that never happens.
And when did you start your preparation for the round one, let's say?
Well, I kind of just did like PAT preparation.
Okay.
And then
That's true.
I kind of just like over year 12 summer basically just stayed inside and just did physics.
And any secrets for anyone watching if they want to be a problem-solving wizard, other than subscribe to Z Physics? But what else do they should do?
I think you should just literally just do a bunch of physics and dedicate as much time as you want to it.
Absolutely. So it seems that the secret is just grind.
Yeah.
Also, actually,
Yeah.
no, for physics BPhO round 1 and round 2. There's also like the astrophysics Olympiads, which obviously are different, but like it's more problem solving, it's more physics and astrophysics type questions could come up in probably more likely in BPhO round 2. So those are good as well, and then you can do the astrophysics Olympiads and also Isaac Physics.
Isaac Physics.
And then you can do, there's also like the Senior Physics Challenge in year 12, which like if you've done that many questions to get there is good practice. And I think actually you did it.
Yeah, I did.
Like 3 of us did it and are now
OJAS
here.
also did it, like,
Did Odas do it 2 years ago?
Yeah.
Oh, that's amazing.
Yeah.
So like then you already start meeting people who are really good at physics. So then, you know, you get inspired.
Are you guys doing physics at university or
I'm doing maths at uni.
maths at uni? Okay, yeah,
Yeah.
solid choice.
I just really enjoy it.
Yeah,
I
same here.
enjoy it just being purely theoretical and
Yeah.
the detail that you can get into it. And I don't know, it's
Fantastic.
just for me.
I'm going to study physics next year.
Yeah, I'm doing like physics / natural sciences, so
Okay,
just sciencey in general, but
Fantastic.
specifically physics.
excellent.
I'm doing engineering.
Engineering?
It's like physics, but a bit more applied.
Yep, very, very useful physics.
Yeah.
I'm here with Ojas, who has just finished a 5-hour practical. How was your practical?
It was all right. It was quite difficult, and there's definitely things that I need to improve on, but that's why we're here, is just to get some practice with these practicals before we head for the IPho.
And what's the training camp like?
So this training camp is quite intense, but much more relaxed than the Oxford camp. So at the Oxford camp, we were working for like 10, 11 hours a day. But here it's mainly just 1 5-hour practical in the morning, and then we have like 2 sessions of theory, which are both about 2 hours long or so. And it's much more focused on just getting practice with doing difficult experiments and difficult problems, because we really need to push ourselves, because obviously the exams are not meant to be easy, we're meant to be really pushed. So we're just getting used to really engaging with those types of problems.
And what's your preparation like to reach this stage?
So I'm currently on a gap year. So I competed in the Olympiads last year, and I was invited to the Astro team training camp. Unfortunately, I didn't make the team, but I was told that it's possible to compete at IPho as long as you're not enrolled in university. And I was planning on taking a gap year anyways, as long as my A-levels were good. So I just decided I'll study for my A-levels, and after that I'll focus on the Olympiads. So throughout this entire year, it's just been solving a lot of difficult problems and trying to really understand the concepts at a deep level, because I think that really helps when you're trying to solve something about an unfamiliar situation. For example, if we're given a problem on, so one of the ones that we had was a capacitor with a variable area, but you don't quite know how the area is changing. So if you've really internalized the concepts about how electric fields sort of work in a capacitor, then it's quite simple or straightforward to see how you should get to the answer, even though at first it seems like I just have this black box in front of me with a sliding plane. How on earth am I meant to figure anything out? And also a lot of it is putting yourself in unfamiliar context in terms of the problems that you're doing. So a lot of the times the problems will be based on something that's like university physics, but you won't have been taught it, or you're not expected to know it at all. But they'll give you all of the equations that you need, and then it's sort of up to you to figure out how does the physics of the situation make sense in line with the equations we're given and things like that.
And did you do a lot of independent preparation outside of school?
Yeah, absolutely. I think with this, it's quite difficult to do in a school environment, because the entire point is you need to struggle with the problems to actually learn the lessons behind them. So, for example, if you just open up a past paper and open up the solutions, you're never going to learn anything, because you'll just be like, oh, right, yeah, I could have gotten that. It's the same thing with these IPho problems. It's like, once you've seen the solution, it's very difficult to unsee it. And you really need to take a lot of time to do these problems. They're not meant to be done in like 5-10 minutes. They're meant to take like 1 hour and 40 per problem with the IPho.
Wow.
So, yeah.
Amazing. And do you have any tips for problem solving? Particularly, there might be somebody watching, I'm sure there's somebody watching who really wants to study physics at university, who really wants to develop really good problem solving skills. Any advice that you might want to give?
So I would say the biggest thing would be really focus on expanding your knowledge of the subject in general. So, for example, if you're curious about something, rather than just sort of ignoring that thought, like really capture it and see where it leads. Maybe there'll be some interesting physics along the way. I think that's one thing where, you know, even if it's just like getting a rough piece of paper and just like trying to do some calculations, looking it up online if you need any help, that's really helpful for building the curiosity you need to really explore these problems at a deep level. Beyond that, just a lot of patience, because, you know, like each of these papers are like 5 hours. If you were like exhausted after 30 minutes, it's difficult, but it's like any other skill. It's just a lot of practice and a lot of patience and a lot of determination to be good at this thing. It's a skill that I think anybody can learn, but as long as, you know, you're consistently working on it, you can make a lot of progress.
Fantastic. And what are you thinking about doing next year after you've gotten your gold medal, obviously?
Well, I'm doing physics at Oxford, so I'm just looking forward to studying more physics, more advanced physics, because of course the IPho syllabus is limited to a certain extent. So it will be interesting to read about more concepts at a more rigorous level and see some of the concepts that I've sort of explored very briefly in this year to sort of develop on that.
Side note, but for anyone who's also applying to Oxford, you obviously would have done really well on the PAT. Any advice on how to prepare for this?
I would say, again, because it's a lot of problem solving, although now it's sort of moved towards a more multiple choice style of question.
Yes, there isn't a certain overlap between the two.
I would say just keep on practicing past papers. I know I've said this multiple times, but I will always stand by this. I think just having the stamina to work through an entire paper without getting tired and really focusing on the sort of resilience. There will be problems that you can't solve. There are problems that I still have no idea how to solve. But, you know, I don't look at that and get upset about it. Instead, I look at that and be like, that's more sort of motivation for me to go and study more and to sort of understand how you can solve a problem like this.
Fantastic.
So, yeah, I think, just one more thing.
Of course, yeah.
I did, because I applied to Oxford the year before as well, but I didn't actually get an interview, unfortunately. And so I decided I wanted to take a gap year because I felt Oxford was a really good place to further my study. And this year when I did it, I did every single past paper like 3 times.
Oh, wow.
And sure, it was a little boring because once you've seen the same problem 3 times, it's like, you know. But I felt like a lot of the problem last year was not actually solving the problems. I was already able to do that. It was the exam technique and really focusing on how I'm laying out my answers and my working, things like that was important. This year, and of course now with the multiple choice, it's not as relevant, but I would still say, like, do every single paper that you can get your hands on multiple times and really make sure that you're improving every time, because that shows that you've actually learnt from your mistakes.
Or as in, like, do a past paper and then redo it and see whether your result is higher.
Yes, but I would say, like, space them out somewhat, because obviously if you do them like back to back in like a few days, you're going to remember exactly how to do it. But if you do it in like a few weeks' time, when you're sort of vaguely forgotten the questions and you look at it again, it's like, I know how to do it this time. I think that was very helpful. So the idea of the problem is you have a body of water, and at z equals 0, so we're taking z to be the height, the speed of sound in water is c, and as you go up or down, the speed changes linearly in both directions. So if I go up, it's c plus bc, and below it's c minus bc. So the speed of sound graph sort of looks like this, if the speed of sound is on this axis and z is on this axis. So it's increasing in both directions. And we're sending a pulse of sound from z equals 0 upwards. So if I just draw the diagram here. So if we take this to be the x-axis and this to be z, we're sending a pulse of sound up at an angle of theta naught to the vertical. And we want to find the trajectory of the water, and we want to find out some facts about how the sound propagates. Specifically, it turns out that this arc is actually a circle when the speed variation is linear. And we're just trying to see if we can figure out a nicer way of doing it. The standard way is to split the path into small segments of dx, of height dz, and using Snell's law over this entire body to figure out that the tangent is, if it's at an angle theta, you can use Snell's law at this point and this point, even though the speed of sound is changing. The reason is because if I consider a series of layers, sorry, the layers are terrible. If I take a bunch of small layers and I put a light beam in, it's going to change gradually between the layers. But it turns out that sine theta, where theta is the angle to the incidence angle, over the speed of sound or light or whatever, is actually a constant. So what you can do is you can say that over this entire path, I know that c at this point over sine theta naught, or sine theta naught over c, is going to be equal to sine theta over c plus bz. And based off of that, you can write a differential equation for dz and dx, and then solve it. And based off of that, you get the answer. However, we were thinking of another way, where if you can draw the trajectory like this, and say that its radius of curvature is r, if you can show that the radius of curvature of the trajectory is a constant, you can then prove that it has to be a circle, because that's the only shape that can actually have a constant radius of curvature. So we were just trying to figure out how to sort of mathematically prove that.
So, using Snell's law, we've already related the angle to the speed of sound in the water at any height. So that's our initial conditions. And then at any point, sine theta over the speed of sound, which we've been given as c plus bz. So because we want an angle theta of 90 degrees here at a height zs, we can substitute this in. Sine of 90 degrees is 1, so sine theta naught over c naught equals 1 over c naught plus bzs. And then we've got an equation here. We can just rearrange it slightly to an easier form of c naught plus bzs equals, c naught over sine theta naught. And then we've found our equation like the question asked us, and we'll go on to use it in the later parts of the question.
So what's the problem like?
The problem is it's to do with sound propagation in the sea and how it varies with height, and basically showing that sound, when it travels underwater, it travels in a circular arc due to it refracting as the speed changes with height. And our task is to show that it does follow a circle and find the radius of that circle.
And how do you go about doing this?
Well, so you use kind of something that you usually use with light, but you kind of take from sound, which is you kind of have to. You can't necessarily prove that that's the case.
Are you talking about the principle of least time?
Yes, but it's not entirely obvious that that applies to sound. I think it does. You use that and alongside some kind of geometry and things like the speed as a function of the height and so on and so forth, and you can combine those to find some kind of equation relating to a circle which has a radius term in terms of the constants that you're given.
I'm here at Cambridge University to observe the preparation for the International Physics Olympiad, and I'm here with Dr. Anson Cheung, who's responsible for preparing the team for the International Physics Olympiad. I've just attended his theory sessions. They're absolutely mind-boggling. I've really enjoyed them, and I'm super excited to share what he has to share with us today. Just a little bit of background about yourself. You competed in the International Physics Olympiad as well?
Yes, so I was a student before 2000. So before the millennium started, and I did the International Physics Olympiad. I'm fortunate to have said I won a medal, okay? Fantastic. And that I've been keen to stay on. So it's one of the things where the community is a very nice community. If you've taken from it as a student, then it's really nice to give back. So ever since I became a student, I also love physics. So of course, because I love physics and because I love giving back to the community, I've stayed on. So I helped write questions, I helped do the training, and now I'm one of the trustees of the Physics Olympiad Committee.
And what was your preparation like when you were a competitor?
Well, first of all, nowhere near what students are doing now. I think the whole process has become a lot more professionalized, simply because the number of resources you can get online has just completely exploded. But in my day, even getting onto the internet was hard to download past papers. you only got past papers by your teachers giving you past papers. So in terms of resources, I didn't have much. So what I did was essentially I did A-level preparation. So it's making sure I knew my A-level material well. And my physics teachers at school, I had some really lovely physics teachers who really, I still admire to this day what preparation they did with me by giving me the right questions to think about, asking me the right questions. And so they gave me a lot of questions to think about and tested my understanding. And it was based around the A-level material. And then with that A-level material, we also did some step physics questions. So I know these days there's no longer any step. There's only step in mathematics and only step 2 and step 3. Step 1 has been depreciated, but step physics existed in my day, and it was doing a lot of step questions and doing a few, but not many, IPho past questions.
And what advice would you give for any A-level students that might be thinking about taking the round 1 next year, but they may be a little bit hesitant, maybe they found the questions a little bit hard when they've looked at them? Any advice on how to prepare and how to enter?
Yeah, the first thing I would say is that nothing in this world comes easy without work, okay? And so if you want to do well, you need to do some work, okay? But you should also try and enjoy yourself, because if you don't enjoy yourself, you're not going to do well. And indeed, in the process of preparing, i.e. doing some past paper questions, you will see whether you want to actually do physics. There's a difference between admiring physics, appreciating physics, which I think is important to do, and actually becoming a physicist. So in the same way that I really like art, I love going to art galleries and looking around. By going to art galleries, that does not make me an artist. I might be able to critique it, I might be able to give some free phrases, some words, some commentary, and pretend to be an artist, but it doesn't make me an artist. At this stage in your life, when you are students, especially in the sixth form, but also before, when you want to decide what you want to do for the rest of your life, and you've decided you want to be a physicist, then that means you have to do physics. And doing physics means studying. Studying means sitting down, okay? It does mean sitting down, looking at resources, looking at questions, and thinking and spending time doing those questions. And the next thing I would say is be really patient, because it is not trivial. Physics is very subtle, but it's not malicious, to quote Einstein. And what you realize is that even simple ideas have a lot of complexity associated with it the moment you dig in, and that you're not necessarily, these things take time. If you think about what we do at university, I say this to my university students, we have 400 years of physics that we teach you. So if you look back and ask, when did Newton do his work? When did Galileo do their work? What's the starting point? Well, that date to now is about 400 years. The undergraduate course, typically for most universities within the UK, is 3+1, namely 3 bachelor years and 1 master's year as an integrated master's. What that means is you have a 100-to-1 ratio of what you're learning. So there's a lot of material that we cram in and give to you. But when you're discovering from the first time by yourself, it takes 1-to-1, and therefore it takes that a long period of time for you to digest and understand. We've shortcut that by giving you the easiest route to understand any particular area of physics. We've made the right definitions. We've given you the right sort of questions to ask to develop you as quickly as possible. Essentially, what we've done as a community is we've given you the roads, okay, or railroads, and then you can easily just follow those tracks. But when you're exploring by yourself, you are going to meander and make all sorts of wrong paths, and that's absolutely fine, and not be worried about that process.
And what are your specific tips on developing problem-solving skills for Olympiads? I've been observing a lot of the sessions here, and I've been absolutely amazed at the work that the British Physics Olympiad team is doing. It's honestly the best problem solving I've ever seen in my life. And how do you develop the habits and the intuition of the students to tackle these incredibly difficult, non-intuitive problems that come up in the International Physics Olympiad?
Well, first and foremost, there's no royal route, okay? To quote Euler, there's no royal route to mathematics. And it does require time and patience. So first thing to note is that when you're solving problems, if you're going from GCSE, typically a GCSE question may take a few minutes. Mm-hmm. And if you think about how long a PhD takes 3 years. Okay, so not all students will get to a PhD, that's fine. So you're moving from a period of a few minutes to do a PhD, which may be 3 years. Okay, and that's to do one problem. Well, A-level, maybe A-level, you're looking at 5 minutes to do a question. So Olympiads, typically you have 3 hours to 5 hours, depending on particular Olympiads, where you have to do only a few questions. So first of all, you need to have patience in the actual problem stage. When you solve them, it will take serious number of minutes, if not hours. The amount of time you need to spend on a problem at GCSE typically is a few minutes. And when you get to Olympiads are typically 3 to 5 hours long, and you only get to solve a few problems there. And so you're moving for maybe a few minutes to maybe an hour or so to do one problem. So you need to have patience, and when you're training, you're not going to do those problems immediately. And so patience is one thing. The other thing is a lot of practice. A lot of practice with things which are just beyond your level of difficulty. So my analogy to this is playing chess or playing tennis or any sport or any game. You want to play with people who are ever so slightly better than you, so that you get something to learn, someone to learn from. But you don't want to do it at such a high level that you end up failing every single point. It's really bad to lose 100% of your tennis matches or 100% of your chess matches. That's a really demoralizing thing. But if you win 100%, you're also not going to learn anything. So you need to find something which is just beyond your level of difficulty, and then understand where you're failing and then do better next time. And everyone has a different threshold as to what the win-loss ratio is, and you need to work out what that win-loss ratio for you is. Okay, sometimes for some people, they might want to win 50% of the time. Some people might need to win 80% of the time. So you need to do problems which are aligned with that win-loss ratio, so that you're happy with feeling confused, but not getting too worried about being confused. Because most of the time, you're facing things you don't know how to deal with. That's fine. That's the whole point about solving problems. If you knew what you were doing, it wouldn't be a problem. Okay, the fact that it's a challenge or a problem, and that's why we like to use the word like physics challenge or problem, is because it's a game that we want you to play. It's wrapped up in a way that we know is possible, but is just beyond your level of immediate ability to answer. And so you need to have fun in doing that, patience, and then trying things which are just beyond your level of difficulty.
And what would you recommend about using mark schemes? Because obviously there is the temptation, okay, here's a problem I can't solve. I thought about it for 2 seconds. I'm going to have a look at what the mark scheme says. Do you have a rule that you might want to give to the students? How should they use mark schemes? Should they use them sort of after a considerable amount of time studying, or if it's a new concept, should they try and learn from the mark scheme, the new concept?
I hate mark schemes. I think they are one of the most horrendous things, which give the illusion of learning, because it shortcuts the process. You can learn only by being stuck and gaining the insights. Okay, but of course you still need some feedback. Okay, you can't learn without feedback. Are mark schemes the right way to have feedback? I would say, unless there's no other alternative, you should try and use something else. Okay, what are the other things you should use? Doing things alone, I think, is really quite demoralizing. Okay, I think you want to do physics training with a teacher. So the best thing is to have a teacher who can help you in school, but also set up a club with your friends. Okay, discuss ideas. That's how research is done. What you don't realize is the lone genius, the Einsteins of the world, well, that's a one-off. Most physics is done in a highly collaborative way. And what that means is we work in a group. Okay, I bounce ideas off you, you bounce ideas off me. There will be other people who are interested in problem solving. Okay, see if you can find someone either locally in your school, in your class, or alternatively online, and work together at solving problems. And don't just look at the answer. Okay, you want someone slightly more experienced than you, perhaps, to sometimes knock ideas against, and they can say, oh, here's a hint. This sort of problem can be solved using this particular technique. Okay, and then you can look up that technique. You don't want to actually just look up the answer, because then what you have lost is the ability. The hard point about any problem is the very first starting point. Okay, the rest of it is relatively straightforward. So once you've got the initial idea, oh, you need to use energy, for example, in this question, then having written down that equation, the rest of it is mathematics, and you turn the handle, you can get the answer out. What's hard is the very first step, and you want someone to essentially give you a hint as to, why don't you consider what things might be conserved in this question. Okay, then you can say, oh yes, energy is conserved, and let's now use energy as a principle. But then you're not given the answer as to what the individual bits are to put into that equation. Whereas if you look at a mark scheme, the answer will say, here's the equation you're using, but you don't necessarily understand the motivation, and it's the motivation that you're looking for. The other big hint I would give you is that once you've solved the problem, that's not the end of it. That's only halfway through. What you need to do, whether you're successful at solving a problem, whether you're not successful at solving a problem, you need to go back and look at what exactly have you learned from doing this problem? What's the bit of physics you've learned? What's the bit of mathematics you've learned? You should always be able to look back and say, could I have done it in a slightly different way? What other insights? Can I take what I've learned in terms of where I've gotten stuck and use it for a new question? Is there a success I can use and say, oh, this is a really useful thing? And you build up your repertoire, your toolkit, okay? And your toolkit might be, you're really good at doing this type of question because you know how to do calculus very well. In fact, there may be another way, non-calculus way of doing it, but then you can look back and see that this problem can be done by calculus, this problem can be done by trigonometry, and then when you're facing a new problem, you've now got multiple toolkits. And knowing the answer means you can go back and solve it in a different way. And indeed, where I would say it's quite useful is that if you do have a problem, distinguish between the mark scheme giving you the method and the mark scheme giving you, say, the numerical answer at the back. Because if you've got the numerical answer at the back, you know at least where you're headed towards. Okay? If there's no numerical answer at the back, what do you do? Okay, well, sometimes you can make some guess or some estimate. Okay, you can even Google and find example questions which are easier for you to tackle. And if it's easier for you to tackle, then you can build up to the question you actually wanted to solve. So it's that climbing the mountain slowly, and then when you've gone through those small steps, eventually you can solve that really hard question that you couldn't do at the end.
Do you think there's something in particular that might separate gold medalists from anyone else on the physics Olympiads?
Yeah, so there are lots of ways of being successful, and there's no unique way of getting a gold medal. But I think there are some common traits. So one of these is a degree of practice. So if you don't practice, then you don't do as well. So it's one, practicing, and two, having some mental resilience, knowing how to cope with things when you fail, because you will fail at certain points to solve a problem, okay? But then how do you pick yourself up and not getting too flustered? Because then if you're flustered, then you can't do the next question, because in general, there may be, say, 3 questions on the Olympiad. And if you're flustered on question 1, then even the question 2 and question 3, which could have been doable, you're not in the right mindset. It's to sort of say to yourself, okay, fine, great, I can't do that part, but maybe I can still tackle the next part, okay? The next thing is to think systematically and write down sensible things, okay? Even if you can't solve a problem fully, I'm sure there are sensible things that you can say about the problem, okay? And then the next thing is to have that patience. So it's a degree of mental toughness, that tenacity, as well as obviously practice. You don't have to be super intelligent, okay? Because the problems have been set by humans. They haven't been set by nature. They've been set by humans, and they've been wrapped up in a particular way. If you're able to just get over that mental hurdle of the fact that this is difficult and say, I want to enjoy it, I just want to understand the physics, then you don't put as much pressure on yourself. So the analogy I like to give here is I play some tennis, and sometimes if you're given too much time to make a shot, you mess up. But if you trust yourself with the practice you've done, you can rely on the instinct of you playing a particular shot, and you don't have to do that thinking. And so some of it is basically knowing that if you've done your homework, you can run on autopilot and managing your expectations. And in terms of doing the prep, obviously that means understanding the physics fundamentally well. You're not just memorizing formulae and doing plug and chug, but you understand what the equations mean and how they relate from a physics perspective. Being able to look at a problem from multiple perspectives is a really useful thing. Looking at it from a graphical perspective, a mathematical perspective, a physical perspective, and knowing how to tie those things together and understanding the core concepts in a deep way. Why is momentum conserved? What are the conditions when it works? Because invariably with the Olympiads, they're working at the limits of the standard problem set, okay? If you're looking at an A-level question, invariably, you know momentum has to be a question in this paper because you know the syllabus. It says momentum is tested in this question paper, and they need to test it in the standard framework, in the most likely framework. But in the Olympiad framework, they're testing it at the limits. So therefore, maybe, in this case, momentum doesn't apply naively. How does it break down? Oh, because there's an external force. Well, in that case, there's a net force. There's a net force. What happens? There's now a rate of change of momentum. So how does that change the momentum formula? It's one of those things where it means you can't just use the formulae blindly. You need to understand where things work, what are the assumptions, and then how to actually apply them in the particular context you're interested in.
Given the wealth of your experience, given that you also are a practicing research physicist and you have, in a way, done it all, do you think there'll be some differences on how to prepare to be a physicist versus how to prepare to be a medalist at an international Olympiad?
Yeah. So there are real differences between a real physicist, a practicing physicist, and someone who solves Olympiad problems. There's obviously lots of overlap. To do both, you need to understand physics. You need to enjoy physics and you need to understand physics. But they're not the same thing. So I view Olympiad problems as fun things to do, and you should treat it as fun, okay? Just because you do well or do badly at Olympiads does not necessarily mean that you'll be bad as a physics researcher, okay? Obviously, there are commonalities, but it doesn't mean that if you're bad at doing Olympiads, you'll never make it as a physicist. And just because you're good at being an Olympiad level medalist does not mean necessarily you do well as a physicist later on, okay? So that's the first thing, okay? Because they are similar but not identical in terms of skill sets. An analogy I'd like to use is the Olympiads might be like solving crossword puzzles, because crossword puzzles enable you to test yourself against the crossword setter. Okay, so the crossword, the cryptic crossword, is wrapped up in a particular way. You need to translate the mind of the crossword setter, and then you have to have a wide enough vocabulary in order to then solve the problem. Okay, but fundamentally, it's solving a problem which is wrapped up in a nice way. It's nicely tied up. Research is not like that, because you're facing the universe and trying to understand the universe, and there's no person who set the problem for you. Okay, so that's therefore different. And so maybe you're able to do crosswords well, but that does not make you a good writer, for example. So the analogy might be crosswords versus writing. In order to write well, you need to have a wide vocabulary. But having a wide vocabulary and being able to solve a crossword does not mean you can write. Okay, and so it's the same thing with being a physicist. It's obviously good to have a physics understanding, which you can get by solving problems, and problem solving is necessary as a prerequisite. But the amount of time you get to solve a crossword puzzle might be a day before the solution is published, or Olympiad questions where it's set to be a certain number of hours. But fundamentally, when you're doing research, you're taking a very long period of time to really get to the grips of it, and then you can ask auxiliary questions or working collaboratively. And in working collaboratively, you can ask questions, you can get hints, whereas when you're solving Olympiad problems by yourself in competition, you don't get any of those hints. You just have to solve the problem as is. You don't have experimental hints. You don't have things that you can try out. Whereas when you're doing real research, you're guided and you're motivated by experiments. And you're guided and motivated by computer simulations. Maybe you can't do the algebra and you need to rely on a computer to do it for you. Well, that's what real research is. Real research is using all the tools at your disposal and having the time to do it and having the patience. Whereas Olympiad problems are doable within the framework of a few hours. So fundamentally, it's a slightly different skill set.
I'm here with the German team leaders for the International Physics Olympiad. They're ex-students who have gone through exactly the same process, have gone to Olympiads, have done really, really well, and are currently studying at university. So would you guys like to introduce yourselves first of all, and maybe what do you do at the moment?
Yeah, I'm Johann. I'm currently a first-year physics student at the University of Heidelberg. And last year I still participated in the national competition, the German Physics Olympiad. And yeah, this year I'm team leader for the current national team.
Fantastic.
Then my turn. I'm Luke. I'm in my second year studying in Ilmenau, small town in Thuringia, mathematics. And 2 years ago I was in the national team of the IPho for Germany, of course. It was quite fun, so I'm here again and as a leader.
Did you end up getting a medal as well?
Yes, I got a bronze medal.
Fantastic. And one of the things that I'm really curious is, what was your experience preparing like for the Olympiad? Like, for instance, when did you start preparing? What sort of things did you do? Did you use any particular books? How many problems were you solving? How much time were you problem solving? Do you reckon? Basically, all the secrets to help as many young people as possible.
So I only got into competitions like in my last year of school. So it was like rather time sensitive to get really good really fast, and to also learn all the stuff you have to know, because there is a lot, not only problem solving skills but also like physics stuff you have to know. It goes up into like third, fourth semester in Germany, like that's second year in university, to even get to know the stuff you have to know to be able to solve problems. And yeah, I just got a very big physics book my father had in his cellar, and
remember which one was it?
Paul Tipler.
Paul Tipler, Tipler, classic.
Great book.
I also recommend it. That's a big book.
It's a very big book, and it's like 1,500 pages. And I just went through it and tried to memorize everything, learn everything, and of course apply everything into practical problems. And then old Olympiad problems, old German Olympiad problems. That's basically most of the things. So most of the time you actually spend practicing, you should be problem solving, and you should solve many problems, and you should solve hard problems, easy problems also, but you progress and get harder and harder, because EPho problems are very, very hard.
Do you ever revisit problems, as in like, here's a problem, I solved that like a year ago, but I don't really remember how to do it, or did you approach problem different ways as well?
So I've never visited old problems, but you can always recommend to, or it's always recommended to it's always recommended to try to approach problems from different angles, because not only do you get like different methods, techniques you also can apply to other problems, but you also really understand the physics behind it, and having a good understanding of physics and the physics behind problems, because problems are often very similar in some ways. So if you kind of really know the physics, you often, and you know many methods to solve problems with certain involving certain physics, you often can just apply a technique you've used before and solve the problem fairly quickly.
Fantastic. And any tips from yourself?
Well, I don't have any more to add to that. My personal experience was a bit different. Like, for me, the biggest help in getting into the IPho team was probably just one of the pre-finalist rounds, because we had sessions on the off days after we did the exams. Exams mostly about experiments and about thermodynamics in a depth that I haven't got in school, helped me really with understanding certain concepts, or even understanding where to begin learning about certain concepts. But for me, the biggest help was actually just being in one of the pre-finalist rounds, actually doing experiments we haven't done at school, and thus learning how to do them.
Did you guys work in groups? One of the things that I really liked about for the physics camps when I used to go in the past, and also here, is just the opportunity to work with other people, which I think is really important. Did you do a lot of, well, I'm sure you would have done a lot of studying by yourself, but did you like supplement like problem solving with other people in camps, and kind of what we're doing in Cambridge at the moment?
Well, I might be an odd case, because I'm not that sociable, so I don't know that many people that did that, but it might be different for you.
Yeah, so I think preparing for Olympiads, or in general learning with other people together, is one of the most effective and just one of the best ways to learn stuff and solve problems, because first you always see the problems from different angles. So being able to explain those different angles to each other and trying to understand other points of view really gets you a new So I prepared with a very good friend for the IPho, and yeah, of course we motivated each other, and also like explained things to each other. Both like understood certain things easier than the other one, and then it was very nice synergy.
That's really, really cool. And any last minute advice that you might want to give to... Actually, I wanted to ask you something else before. So it's quite interesting because you guys have chosen the 2 degrees that a lot of graduates are thinking about, because a lot of you guys watching were probably near the end of your studies and you might be interested in both mathematics and physics, and it's a difficult choice, isn't it?
Yes.
How did you end up choosing mathematics, for instance?
For me, my a bit trivial thought was basically like, yeah, I start with mathematics. If I have enough leftover time, I can just do physics on top of that. And sort of like doing a dual study or similar. Then it over time changed to the thought of like, yeah, I can compress my maths studies and, I don't know, take a year less than I expected, and then I have more time to do physics afterwards. But I think it's mostly just, for me, the reason I started with mathematics was just when I think when you understand mathematics, then it's much easier to learn about difficult physical concepts, because at least for me, the most difficult part in physics is the underlying mathematics. But yeah, I can see there are people with different views.
Yeah, I'd say my view is exactly opposite. I'd say if you understand the physics and you have an intuition for physics, you often also understand the mathematics, and you understand the mathematics often from a whole other level. Take differential equations. If you have a differential equation in math, it's a very abstract thing. You kind of have a derivative, second derivative of some function, and you're trying to find the function, which is very abstract, very difficult. And if you start viewing those as, for example, velocities, accelerations, or really like any other physical quantity, often even by just looking at the differential equation and asking yourself what properties it should have and what properties the system should have, you often get an intuition of how the solution should look like and how the math works out. So I think if you like to think very abstract, mathematics is good for you. But for myself, I like to start with concrete examples and like abstract, get more abstract on the way. Yeah, and you can, so it both ways work. It kind of depends on how you like to think.
And what's first year university like? Do you guys think that your Olympiad preparation has helped you in your kind of year one of your studies?
Then I thought, well, I think at least for me, it hasn't really impacted me all that much apart from analysis, because like at least the way we study mathematics, where I study, it's a whole different beast than school mathematics or Olympiad mathematics. So yeah, there was not really that much to be gained. But something that transferred over from Olympiads and similar is the way of logical thinking. Like, no matter what setting you're in, if you're in mathematics or in physics or in most natural sciences, when you're given a problem, then if you have a good logical understanding of logics, I don't know, then you have probably an easier time to solve that problem. And that does transfer over from Olympiads and similar.
I think also you develop this kind of like special tenacity, because I mean Olympiad problems are pretty hard, so when you encounter something hard at university, you're like, it's okay, like with we've struggled before, so is it just another struggle?
Getting used to it.
Yeah.
I think that's also one of the most important things you learn, and one of the most important things you have to learn when getting started with Olympiad problems and like those competitions. The problems are often very, very, very hard. And when I started out first, many, oh, I pressed something.
That's okay.
That's okay. Does it still work?
Yeah. Probably. I'll just leave mine here just in case.
Okay.
Yeah. Can I just see for a second? Yeah. Oh yeah, it's still recording. Hello? Yeah.
Okay.
I might leave that in.
Yeah. So if you start out with Olympiad problems, you often face very difficult problems, and just being able to have that mindset that you can actually solve those problems really even helps you in solving the problems, actually, because like when I first started out, I sat in front of a problem like 1 hour and I was like, I can solve this. I have no idea. I'm gonna try something. Oh no, it doesn't work out because I'm too stupid. But I think most of the time, if I actually had worked out my ideas, it would have worked. So if you face a difficult problem, just try to work it out, play with it, try to simplify it, of course. But most of the times, it's easier than it looks.
So, lection. What you can learn from this for Olympiads and for studying later, build your tenacity.
Yeah, I couldn't agree more. I honestly think it's probably just this video is just general life advice, not just Olympiad advice.
Everything in the life of an life is an Olympic.
I think this is a fantastic way to end, actually. But yeah, thank you so much for taking the time to speak to me. I really appreciate that. Good luck in your studies. And yeah, when you get a Nobel Prize and Fields medal, in a couple of years, come back on the channel. It would be great to interview.
Sure.
I give you a shout out.
Yeah, shout out to Zat Physics. Like and subscribe.